Okay, I'm talking to my seventh grade math students, both classes. I've had all kinds of problems today with my computer and recording equipment. And so neither class recorded. My morning devotions didn't record. My Warriors of Christ didn't record. I've had a lot of ACT didn't record. I've had a lot of problems. All operator caused. It's not just making silly mistakes and trying to set it up. Anyway, here we are. I'm going to briefly go over some of these problems that I went over in the seventh grade math classes today, so you'll at least have the problems to look at that I did in class. I'm not going to go over the scripture verses. I'm just going to make a very quick, brief video so you'll have the problems that I worked in class and be able to get the idea. Obviously, if you have questions, ask me about it later. Feel free to ask anything you want to when you get to class, and I'll help you with it. But we talked about scientific notation, and I pointed out that in science, especially, that's why they call it scientific notation. In science, scientists sometimes, especially if they're astronomers or cosmologists, they have to deal with huge numbers when they talk about how far away these galaxies are and things like that. Or if scientists are working with very, very tiny things like the proteins or uh, molecules in a cell, they have to use very, very tiny numbers. And our regular numbers notation, it doesn't work for those kind of numbers. They're so huge or so tiny, we have to use a special kind of notation. So scientists have come up with a notation that they call scientific notation, and it's pretty common in life, and you need to be familiar with it. You'll run into it in your science courses, and you'll run into it in other math courses. So if, for example, you look at a number like this, hundreds, thousands, millions, billions, trillions, 9,461,000,000,000 kilometers, that's a lot of zeros. When you write down a lot of numbers like that, it's easy to drop a zero and it takes up a lot of space. It's cumbersome. It's not very easy to work with. So they write it by moving the decimal place all the way from here to here so that there's only one digit to the left of that decimal place. They move it right in front of the 9. Here it is. And so and you count the decimal places 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And that would be 10 to the 12th power. We worked with powers of 10 earlier. 10 cubed is 1,000. 10 squared is 100. 10 to the 4th is 10,000. So 10 to the 12th would be this many places. So you can write 9.461. The decimal is now right here times 10 to the 12th. And that's the same as this. It's just different notation. This is standard notation. This is scientific notation. So you need to be familiar with that. And here's a few examples. We looked at that in your book. You can look at it if you want to, just to get some illustrations of how it makes numbers look different. These all look pretty much the same. 42 million millimeters is the same as 4.2 times 10 to the 7th. We moved it over 7 places to 4.2. And every time you do scientific notation, there's going to be a number over here and a time sign here and a 10 here and an exponent here. All four of those things, a number right here, a time sign, 10, and an exponent. This number will be between 1 and 10, but not 10. Like it goes actually to the left of the decimal, there will be one digit. It could be a 1, 2, 3, 4, 5, 6, 7, 8, or 9. Cannot be a 10 because that would be 2 digits. You see the point? So you move the decimal place till there's only one digit to the left of it. And then you count the number of places you moved it, and that will be the power of 10, based on what we learned earlier about powers of 10. So 4.62, the decimal times 10 to the 6th would be, you move the decimal place 6 places to the right. When you multiply that by 10 to the 6th, 10 to the 6th is a million. So 4.62 times a million would be 4,620,000. Just move the decimal 1, 2, 3, 4, 5, 6 places. The number over here can have any number of digits, but some of them will be after the decimal point. The left of the decimal will only be one digit. Okay. So if you have a number like 15 million, you're going to have to move the decimal. It's understood to be right here. You see that? You're going to have to move it 7 places to get it over here so that there's only one digit to the left of the decimal. 1, 2, 3, 4, 5, 6, 7. So that's 1.5. You see, you moved it. So there's only one digit to the left of the decimal, times 10 to the 7th because we moved it 7 places. How many places did we move this one? Well, we moved it all the way to here. So there's only one digit to the left. 3, 6, 9, 10, 11. So there's 4 times 10 to the 11th. If you want to say 4.0, you're welcome to do that. But since there's no other significant digit other than zeros here after the 4, it's just 4.0 times 10 to the 11th. This one, I moved the decimal right here, but I can't just say 5 because I don't want to lose that 9, 509. So I write 5.09. Anything that's not a 0, you have to have it in this part of the number, 5.09. And when I moved it 6 places, 1, 2, 3, 4, 5, 6, so it's 5.09 times 10 to the 6. This 6 does not tell you how many zeros there are. In this case, it did because everything was 0 except the 4. 3, 6, 9, 10, 11. But if there are other digits in here, other numbers besides zeros, like this 9, that means there won't be that many zeros. There are only 4 zeros. It moves it 6 places. This doesn't tell you how many zeros every time, but it tells you how many places you move it. If it's written out like this, 250 billion, the thing to do is change it to 250. That would be 250,000. That would be 250 million. And this would be 250 billion, hundreds, thousands, millions, billions. And then you change it to 2.5. So there's one digit to the left of the decimal. How far did you move it? 3, 6, 9, 10, 11 again, times 10 to the 11. Notice the times 10 is always there. Don't leave that out. You also have to be able to go the other way. So when you have numbers that are written in scientific notation in the first place, you need to be able to change them back to regular notation, standard notation. It's the same idea. This 6 tells you how many places to move that decimal, except this time you're moving it to the right to get this big number. So I've got 3.4, and if you want to, make a whole bunch of zeros, as many as you need. You don't need all those zeros, but move it 6 places. 1, 2, 3, 4, 5, 6. Put it right there. Make sure you count carefully. 1, 2, 3, 4, 5, 6. And of course, you don't need all these other zeros. You don't have to write them all down, but if it helps you count, and then 3 of them here, another 3 here, that's 3,400,000. Or you could simply say 3.4 times 10 to the 6. I'm going to move that over 6 places to the right. So I've got 4. There's one place. There's 2 places. 3, 4, 5, 6. Just count them as you write them down. You can do that too. 3,400,000. Here the decimals right after the 5. I've got to move it 8 places. In this case, it'll all be zeros. There's no other number after the 5, just the 5. 5. There's 1, 2, 3, 4, 5, 6, 7, 8. 500 million. Same thing here. I got 5 zeros. 1, 2, 3, 4, 5. But what it really means is I move it 5 places. It just, they all happen to be zeros. 100,000. In the last ones here, you're supposed to tell whether it's equal, less than, or greater than. 1.5 times 10 to the 5th, 1.5 times 10 to the 6th, and they're just wanting you to realize that obviously 10 to the 6th is a bigger number than 10 to the 5th, right? 10 to the 5th would be 100,000, 10 to the 6th would be a million. So there's an extra zero in this number. This is the same as move it 5 places. There's 1, 2, 3, 4, 5, 150,000. This is the same as move it 6 places. There's 1, 2, 3, 4, 5, 6, 1,500,000. So this number is obviously less than that number. A million, well, it's the same as 1 times 10 to the 6, isn't it? Because you could write out a million like this and realize that to write in scientific notation, you'd move it 6 places to the left. 1, 1, 0, if you want to say that, times 10 to the 6. Or you could just write 1 like they did over there. These are equal. All right. I want to do one other thing with you real quickly. Order of operations. Some of you are familiar with this and some of you are not. But there's a saying that we use sometimes. Please excuse my dear Aunt Sally. They've written it down there. Please stands for parentheses. Excuse stands for exponents. My stands for multiplication. Dear stands for division. Aunt stands for addition, and Sally stands for subtraction. And it helps you realize what order to do operations when you've got a kind of a complicated problem. Mathematicians had to come up with this a long time ago so they'd all get the same answer. For example, if I said 3 times 8 minus 2, if I subtracted 8 minus 2 first, I would get 6, and 3 times 6 would be 18. But if I multiplied 3 times 8 first, I would get what 3 times 8 is. 8 is 24 minus 2 would be 22. Now, those are obviously two different answers. One of them's wrong. It just depends on your order of operations. And so they decided that what we'll always do, and this makes sense mathematically, is that we always do multiplication and division before we do addition and subtraction. So you do this before you do this. Even if the subtraction was first, you do the multiplication, even if it was over here. 3 times 8 is 24, and 24 minus 2 is 22. So this is incorrect. You don't do the subtraction first. That's what this tells you, the order of operations. Parenthesis includes parentheses and brackets and braces and even division bars. If you had 3 times x minus 2 up here and 2x minus 4 down here, you do this stuff first and you do that stuff separate from this, and then you divide. This is a grouping symbol that separates the numerator from the denominator. So that's all kinds of parentheses there. And then exponents, you remember exponents, there's a little numbers written above, like 4 cubed means 4 times 4 times 4, which is 64. You do this before you do any of the multiplication, division, addition, or subtraction. So if you've got any exponents in there, go ahead and evaluate them before you start multiplying and dividing and adding and subtracting. Then you do multiplication and division. And really listen very carefully now, this is important. You don't always do multiplication first. If there's both multiplication and division in the problem, you just move from left to right and you do the ones that come first. If division comes first, you divide. If multiplication comes first, you multiply. Just do them as you come to them. We're going left to right, where there's multiplication and division. So they're like a pair. You can go either way. Same thing with addition and subtraction. If you got both addition and subtraction in the problem, and you get to the subtraction first as you move from left to right, do it. Do the subtraction. Then whatever's next. Could be more subtraction, could be some addition. But it's addition and subtraction from left to right. Multiplication division from left to right. But always do multiplication division before you do addition and subtraction. So you've got to remember that order of operations, and please excuse my dear Aunt Sally. It's a nice little memory device that'll help you remember it. So here's some sample problems. If you look at this, I've got an addition, a multiplication, subtraction, and division. What do you do first? Well, there's no parentheses, there are no exponents. So I'm going to do multiplication and division first from left to right. That means this is the first thing I do. So I've got 5 plus 25 minus 5 divided by 5. There's the first step. Then I've got division. I've got to do it before addition and subtraction. So I've got 5 plus 25 minus 1, 5 divided by 5. Now I've got addition and subtraction only, left to right. 5 plus 25 is 30. 30 minus 1 is 29. Yeah. The next one's just about like it. I'll just skip that one for now. In fact, they use almost the same thing. You just do subtraction before you do addition. Once you do the multiplication, then the division, then the subtraction, left to right, then the addition. Down here, you don't do subtraction yet. You got multiplication and division. Do the multiplication. You get 24 minus 8 minus 12 divided by 4. And then do the division. 24 minus 8 minus 3. You see, division before subtraction. And then you can do the subtraction. Finally, on that last one down there, 2 cubed is 8. Remember exponents? You got a grouping symbol here. That means do all this stuff on the top first before you divide by 3. All this stuff has to be done first. 2 cubed is 2 times 2 times 2. That's 8. Do the exponents before addition or multiplication or division or subtraction. 2 cubed is 8. 3 squared is 9. This is 2 times 2 times 2. Don't say 6. It's 8. Don't say 6. It's 8. That's 9. That's 3 times 3 squared is 9. Plus 2 times 5 all over 3. Did the exponents. Now I got multiplication. That has to be done before addition and subtraction. So I got 8 plus 9 plus 10. divided by 3. These are grouped together, so I got to do them before the division. Was that grouping symbol? 8 and 9, 17, and 10 is 27, divided by 3. And I get 9. End of the problem. Okay. I'll do this next time with you when we're in class again. So there's kind of an abbreviated, quick review of what we did in class today. That may help you study and get ready for doing these problems. Okay. God bless you guys. Have a blessed day.